Okay, this is one of the most important chapters. This is the fundamental techniques that we should control, and then we can discuss in more higher level. So this is about linear algebra. Let's make a quick review about linear algebra and the vector space. Someone said that one of the most important discovery quantum mechanics in 20 years was Albert Wolnam's in his mathematical foundation of the can be described by linear algebra. All of them can describe because of the Heisenberg's work masterpiece. So this is about vector. What is vector? It represents something in a space that in some some dimension that in each dimension there are some numbers, either complex numbers or the real number. I think it's just about represent in that dimension what it represent for how long or what is the direction and so on. And these are just very interesting. So there are notations like a little numbers, and these are scalars, and so this very but we should also focus on the special ones that zero, ones, and unit vectors like this. There are some basic operations. The notation used to is that is used to the dot double dot equal means it denotes the denote equality. That is true by definition and not by happens but I mean that it denotes the equality that is true by definition, not by happenstance. And that's how geometry understanding that is we have some laws and some so it's about the scalar multiplication. So in linear, so we can this is the basic operation. And the other things are the scalar vector multiplication, the property. And also there are linear combination is very basic. That means that in this system there are two laws that scalar and addition there so that the combination doesn't change its basic law. The norms means it is a measurement about its quality, property. And dot product means that dot in each dimension, each pair will multiply together, and then to be a new new thing, new what new to come to two vectors multiplication, we can get a new vector. Oh, it's a new vector, but this is a self product, dot product, and inner product means that It is just like a norm, square norm squared. That varies dot products rather than multiplication. The algebra models and the overlaps of the two vectors in a product. Oh, it's not the so sorry. When they product each other, we can get only one number. I think it's just like collapse. Oh no, not a great metaphor. Metaphor. Outer products means that it's just a complex number is what is that. Another dimension is I, so that we can use it to represent the in another direction, which means that I squared means -1. Oh, -1 squared is I think this expression is well. Some number, real number, rational number, integral whole numbers, like the norm of the complementer is that some basic comparison and operation. Also, there are another inner products. Very similar. So what I want to polar means what the polar coordinate and some unit conveys very easy Euler's formula, and this is another combination transformation from the exponential to the sin cosine. There are some basic matrix operations. Basic matrix basic matrix operation. Basic matrix operation means that poly x, poly y. Oh, poly z, poly y. Oh, there are. I think these are some representation we need to remember. We need to recognize the poly operators. Also, it's about transform space. Matrices transform space. Matrix doesn't merely transform particular to a set. It transforms an entire vector space. We multiply them by like this. Multiply the vector by the matrix. Poly Z, poly Y, poly X are the different representation of the different two times two matrix. Oh, what is the matrix transform space? A matrix is a more fundamental object on linear transformation. Linear transformation, matrix multiplication means that we can do some transformation between matrix and matrix. So this is for example, there's a 1, 2, 3, 4, 5, 2, 2, 2, 3, 2, 2, 2, 2, 3, and then we can get 1, 2, 3. Oh, there are some rules, operating rules. It's very easy, and the same size means that NP, NM, NP, M times N times P, M times P, and identity means that there are several. Identity means that this is one matrix times it, and it's orange. Orange and the term transpose Turing rows and column and then vice versa. Also, there are different conjugate means that. Oh, I think it's a very important concept is conjugate in matrix. How to conjugate a matrix? Just conjugate each of the matrix. Just conjugate each of the matrix, and oh, this is the there is another denotation that notations means. I think how to say that a oh there is a name too about this notation. It denotes a conjugate transposition. Um, the conjugate transpose and inner product means that when transport them. Oh, inner product means that give to in the complex world. First we can conjugate transpose and then to do it. Oh, this is some mathematical expression that giving two vectors. What we should do to represent the inner products. You can already notice that. Oh, this is rules which we may express using our recently developed notation for transpose as follows, and we must further adorn this expression with our new notation for conjugate, and then there are some inner product, like inner product means what? All in all, we may compactly express the inner product of vector u and simply u bar transpose times v. Fantastic. So in summary, we have the following equivalent expressions for the inner product of two vectors. Oh, this is a notation bracket and key notation means that this is just an inner product that is the bracket means that the column is equals to the column and the transformation by we can refer to the u dash I think. So we can do some notations like this. Oh yeah. Oh, brain cave means that this is just some conjugate transpose. We'll show you you could recurrent transpose the matrix Y and then conjugate transpose Y and conjugate and computational matrix conjugate first and transpose or transpose convenience of unitary. Unitary operators is an operator whose inverse of is its conjugate transpose. Oh, that when we conjugate transpose its inverse is so the inverse times the inverse times the u dash u inverse times u dash is identification. This is important because quantum states are represented as vectors with one norm one in a Hilbert space, and we can define a norm or less, which is a function. So there are some traits like the main diagonal unitary operator. Unitary operator. Oh, I don't know. I just know about what is the meaning of this mathematical notation, but what know how to connect them with the qubits, superposition, state, and so on. Let's make a further explanation that this is important because quantum states are represented vectors with norm 1 living in a Hilbert space. Oh, I don't know. So integral operator presumes the norm of the vector on which it operates. So unitary operator to vector whose norm is 1 is vector whose norm is also 1. Let's repeat the application of a unitary operator to a vector whose norm is 1 is a vector whose norm is also 1. Mm. I don't know the meaning of the application to a vector. Norm, why is 1 is a vector whose norm is also 1, or unitary of data, and that. Norm and length, I don't know. Trace main diagonal means that trace means the diagonal summation. Inner product and urban and trace and the A bracket B means that it has times B. Repeat again. I think it's very important about the unitary representation. 没有到一个呢。The inner product and in R2 U dash times N trace and so on inner product total. Okay. Yes, several inner product computation.